For chapter 2.5, we're covering proof by contradiction, and this chapter is actually pretty small. We're not covering everything in the chapter. We're mostly looking at proof by contradiction and existence or non-existence proofs. So as the book says about proof by contradiction, one way to think about direct proof and proof by contrapositive is that they both demonstrate, in different ways, that there cannot possibly be a counterexample to the theorem. Thus we know the theorem must be true for all elements of the domain. These proof techniques, that is, the direct proof and the contrapositive, are based on two properties that a potential counterexample to a given implication must possess. So first, it must make the hypothesis of the implication true, and two, it must make the conclusion of the implication false. So in other words, remember our P then Q statements. If P is true, but Q is false, then the entire statement is false. And that's the only time it is false. So in the direct proof, we choose an element satisfying property 1, where the hypothesis is true, and that the element cannot satisfy property 2, or it must make the conclusion false, so we cannot find a counterexample. When we show the contrapositive, we choose an element satisfying property 2, where the conclusion of the implication is false, and then the same element cannot satisfy property 1, where it makes the hypothesis true. So in proof by contradiction, we assume a counterexample is found, and we show that it cannot possibly be true because it would lead to a contradiction, a statement that we know to be false. Thus, we are showing that properties 1 and 2 are logically incompatible to the case that we found as a counterexample. Okay, so if we have the problem prove by contradiction, if n squared is even, then n is even. Remember that this is the hypothesis, and this is the conclusion. And so, to prove by contradiction, we have to say that we have found some case where the first part is true, the hypothesis is true, but that the conclusion is false. So what does this mean? Well, we found that n squared is even, but we found a case where n is odd. So from there we translate it into math. So we want to say that n squared is even, so n squared is some even number. But we want to say that n itself is odd. So we'll say n is equal to 2l plus 1. So, to write this just as an equation, we'd have 2l plus 1 squared should be equal to 2k. So, n squared should be equal to n squared. And then we just compute it out from there. So we have 2l plus 1, 2l plus 1 equals 2k. 4l squared plus 4l plus 1 equals 2k. And then really the best way to solve this one is to get all of the constants on one side and kind of just work with it from there so that we show that we don't have an integer afterwards. So let's say we have 1 is equal to 2k minus 4l squared minus 4l. And I'm going to factor out the common 2, so 1 equals 2, k minus 2l squared minus 2. And I'm going to divide both sides by 2. So then we have 1/2 is equal to k minus 2l squared minus 2l. So at this simplified result, we see that this is a fraction, and that is incorrect. It shows that it's a contradiction because we're talking about integers. If n squared is even, an even integer, then n is an even integer. But in this case, we come out with 1/2, and so this is our proof by contradiction. No counterexample exists. And here's the problem again in slide form. So just remember the steps and work on it a little bit at a time. Let's work out some more examples just to see further how this works. So along the same lines, we'll have if n squared is odd, then n is odd. So we have a hypothesis and we have the conclusion. And we'll look at this, we'll have the hypothesis be true. So hypothesis is true, and we want the conclusion to be false. Is false. So we can say n squared is some odd number, so n squared is equal to something odd. And then we'll say n is odd. Well, we found this to be false, we found an n that is even. So we'll say n itself is equal to some even number. And then we just do the same sort of thing. 2k squared should be equal to 2l plus 1. And then we just make that, and then we just simplify. So 4k squared, and I'm just going to already go ahead and move the 2l over, minus 2l equals 1. Factor out the common term, so 2k squared minus l is equal to 1. 2k squared minus l is equal to 1/2. And there we see that this comes out to not be an integer. If we have, obviously this is an integer, k squared, k times k. This is an integer, some integer minus an integer equals a fraction. So this is basically not true. A counterexample cannot exist. Okay, and one more example. So a perfect square cannot have the form 4k plus 2. So let's say that this is the perfect square. So we'll say n squared, some number, when you square it, is going to be equal to 4k plus 2. And then we also have to make a statement about n. So n is just some number. We're going to multiply it by that. But let's go ahead and say it's even, just so we have some way to write it. So some even number squared cannot be this result. But we're going to say that we found it to be true. So let's write this. N squared here should be equal to 4k plus 2. So when we square this value, which is n, we should get something like this out of it. So let's go ahead and multiply this out. This is 4l squared. I'll just move the 4k over already. And we can see that we can factor out a 4. So 4l squared minus k is equal to 2. And again, we're going to do our division by 4 and get the same sort of thing out where it's not a integer that results. So l squared minus k is equal to 1/2. Remember, this is an integer. An integer squared is still an integer. This is an integer, so an integer minus an integer should also be an integer, but it's not here. So this is how we prove that we cannot have this form for a perfect square. Alright, and the other thing we're looking at this chapter is the existence proofs. And these basically are just finding some number that works out with some proposition. So an existence proof is a proof of a theorem characterized as there exists x in some domain such that p of x. So unlike our previous proofs where we're saying for all numbers, we're only looking for one item. Likewise, the proof of a theorem is characterized as there does not exist an x in some domain D such that p of x. That's called a non-existence proof. So if we look at an example question, this is 14a. There exists a positive rational number r such that this is true. When we plug in r, this will be true. Now, this is a polynomial. We can go ahead and solve this, but if we could also just plug in some number, any number that happened to make this true, that would also work. But since this is a polynomial, let's just say 6r squared plus 11r is minus 35 is equal to 0. And we could do the factoring, or we could do the, x equals minus b plus or minus 4. Wait, I don't quite remember the thing. or we could use the quadratic formula to solve it, or we can just go to Wolfram Alpha. So I'm going to type in 6r squared plus 11r minus 35, and I think it will solve this without even me putting equals 0, and it will give me the roots. So in here, here's what we'd end up factoring it to, and here are the two roots, and we can see that 5/3 is a rational number, and it's positive. So just the fact that this exists proves this statement. It's not saying that all roots are a positive rational number, because this one doesn't fit, but this one fits, and so that's basically all the proof we need. All we have to say is 5/3 satisfies this statement.